Hi, welcome to our channel of IGNOU Audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Certificate Programs Postgraduate Certificate, Certificate of Competency in Power Distribution, Electrical Technicians, CCPD, OEE 001 Electricity and Safety Measures, Block-1 Elementary Electrical and Exposure to Tools, Unit-1 Basics of Electricity 1.1 Introduction. Electricity is so closely linked to our day-to-day life that living without electricity would be a suffocating thought to many of us. Electricity, in its commonly usable form, is a manufactured product. It is not something you pump out of the ground or mine or collect from the sun or wind. Electricity is the flow of electrical power or charge. It is a secondary energy source, which means that we get it from the conversion of other sources of energy like coal, natural gas, oil, nuclear power and other natural sources, which are called primary sources. The energy sources we use to make electricity can be renewable or non-renewable, but electricity itself is neither renewable nor non-renewable. Electricity is one of our most widely used forms of energy. Objectives. After studying this unit, you should be able to explain electricity, describe what is matter, free electrons, etc., explain the key terms voltage, current, power, energy, define resistance and impedance. Describe three types of electricity loads, define power system efficiency, discuss power factor and phase angle, differentiate between active and reactive power, and explain magnets and types of magnets. 1.2 Basics of electricity. Electricity is so vital to modern life that all of us need to understand it fully, in order that we can enjoy all the benefits it brings. Most people don't understand what it is. They just turn on a light switch, and there is brightness, or start an appliance or push a button and something works. It's only when there is no electric power available that we start to consider the importance of it in our daily personal and working lives. Let us start with building a good understanding of basic terms and concepts most often used to describe and discuss electrical issues. Please take the time necessary to grasp these basic terms and concepts. To build working knowledge, the materials we observe and interact with from day to day are formed from atoms and molecules that are electrically neutral, having an equal number of positive charges, protons, in the nucleus, and negative charges, electrons, in shells surrounding the nucleus. 1.2.1 Matter. Anything which possesses mass and occupies space is called matter. Matter can be in any of the three forms: solid, liquid and gas. The matter consists of molecules. The molecules are made up of one or more atoms. Solid. In a solid, molecular forces closely bind the molecules to one another. A solid holds its shape and the volume of a solid is fixed by the shape of the solid. Liquid. In a liquid, the molecular forces are weaker than in a solid. Hence, the molecules are free to move around. A liquid will take the shape of its container. However, a given quantity of a liquid has a fixed volume. Gas. In a gas, the molecular forces are very weak. A gas fills its container, taking both the shape and the volume of the container. Plasma. Plasma is the fourth state of matter. In general, we know that there are three states of matter: solid, liquid and gas, but there are actually four. The fourth state of matter is plasma. To put it very simply, a plasma is an ionized gas, a gas into which sufficient energy is provided to free electron from atom and molecules. The matter consists of molecules. The molecules are made up of one or more atoms. Atoms of different types may combine to make a molecule. 1.2.2 Atomic structure an atom is the smallest particle of any element which can be identified. It is composed of smaller subatomic particles. The properties of an element are identified in the atom, but not in the subatomic parts. Atoms are made up of three types of subatomic particles: electrons, protons and neutrons. The center part of an atom is called nucleus and is made up of protons and neutrons. The electrons move around the nucleus. Look at the screen, figure 1.2, structure of an atom. These subatomic particles have different properties. Electrons are tiny, very light particles that have a negative electrical charge, negative dot. These particles spin in around the nucleus in zones called shell, somewhat like the planets in the orbit of Sun. Protons are much larger and heavier than electrons and have the opposite charge, i.e. protons have a positive charge which is equal in magnitude to the charge of an electron. The protons are situated in nucleus. Neutrons are large and heavy like protons. However, neutrons have no electrical charge. These are also situated in nucleus. Each atom is made up of a combination of these particles. 1.2.3 free electrons. The electrons spinning in last shell of the atom are called free electrons. These free electrons can be removed or liberated from its shell by a relatively smaller force. These free electrons are the carriers of electricity. The reason for the free electrons to be released could be many. Example: mechanical, chemical, presence of external electrical field, etc. In the case of a battery cell, a chemical reaction leads to the release of electrically charged ions, which release free electrons onto the terminals of the cell. 1.2.4 Current, voltage and resistance. Electricity is identified by two basic parameters, current and voltage. These two are measurable quantities. Resistance defines the relation between current and voltage in an electrical circuit. We start by thinking about current as the flow of charge. Resistance comes in as a measure of opposition to the flow of charge. Current, the flow of electrons in any conducting material from one point to another, is called electric current. While the electrons move from the negative terminal to the positive one, by convention the current is said to flow from the positive to the negative terminal. Points to remember: current, basic unit, measurement of current is ampere. A instrument to measure current is called ammeter. Ammeter is connected in series with the circuit, i.e. the same current that is to be measured flows through the ammeter. As well, voltage, the electromotive force or potential difference causing the flow of electrons. Current in any conductor is called voltage. The voltage is measured between the two ends of the circuit. Points to remember: voltage, basic unit, measurement of voltage is volt. V. Measuring instrument of voltage is called voltmeter. Voltmeter is connected in parallel to the circuit, i.e. to the two terminal points between which the current flows. Resistance, this is the property of a substance which gives opposition to flow of electrons through itself. If we apply the same voltage to the ends of different materials, the amount of current that flows will differ in each case. Resistance is the property that causes this difference. Higher the resistance, lesser would be the current. In general, metals have less resistance and hence are suitable as conductor of electricity. The most common conductors are copper, aluminium. Resistance is measured in ohm. Instrument to measure resistance is called ohmmeter. Some types of material show very low resistance value. All metals have this property. The material with very low resistance is called a conductor, i.e. it conducts electricity. Some other types of material show value of high resistance. Such material is termed as a non-conductor. If a non-conducting material is used to deliberately prevent electricity being conducted, it is named as an insulator. Ohm's law. Ohm's law is the basic statement of the relationship between the two basic quantities associated with electricity, I voltage and current, and their relationship with resistance. Ohm's law states that, for a conductor at constant temperature, the current in the conductor is directly proportional to the potential difference across it. Imagine a conductor through which a current I is flowing and let V be the potential difference between ends of the conductor. Then Ohm's law states that V is equal to Ri, where constant of proportionality R is called the resistance of the conductor. Its measuring unit is ohm. Current is inversely proportional to resistance. 1.2.5 Power, energy, and efficiency. We are interested in electricity because it can do useful work for us. Therefore, we want to quantify how much work can be derived from it. This capacity is defined in terms of power and energy. Power, remember that power P is the rate of doing work. In the case of electricity, we define it as the product of voltage and current. Power is used to produce real work. Points to remember: power, measuring unit of power is joule second or watt. Power is equal to voltage into current. P is equal to V into I. 1 watt is equal to 1 volt into 1 ampere. Bigger unit of power is kilowatt, kW. 1 kilowatt is equal to 1000 watt. Similarly, 1000 kilowatts equals 1 megawatt. Megawatt, energy, the capacity for doing the work is called energy. To say it differently, it is the rate of doing work, I power, multiplied by the time for which that power is applicable. Points to remember: energy, usual measuring unit of energy is kWh. 1 kilowatt hour is equal to 1000 watt. For 1 hour is equal to 36 lakhs joule. 1 kilowatt hour is equal to 1 unit of electrical energy. It is also known as Board of Trade unit, BOT. A larger unit is MWH, which is 1000 kilowatt hours. Efficiency. In an ideal situation and using a perfect machine, we should be able to convert every bit of the energy fed to the machine to useful work as its output. Unfortunately, in any real-life situation, a perfect machine does not exist. Hence, the output of any machine is always less than the input energy. The difference is usually wasted as unrecoverable heat, due mainly to friction.
The efficiency is the ratio of desired form of energy obtains from a machine to the total energy fed to the machine. A efficiency equals output, useful, energy divided by total input energy. B efficiency equals input energy losses divided by input energy. C percent efficiency equals output, useful, energy divided by total input energy into 100. Efficiency of power system. The efficiency of power system is maximized when the total combined load is purely resistive. Therefore, when the total load on the system approaches purely resistive, the total current requirements and losses are minimum. Total power that has to be produced is minimized. The total power becomes real power, i.e. minimum power required to serve all loads. When efficiency is maximized, then benefits are realized as power losses of system are minimized, extra capacity is made available in transmission lines, distribution lines, and substation equipment because these are rated on the amount of current carrying capability. If the current flow is less, then more capacity available to serve additional load. 1.2.6 Inductance, capacitance and impedance. In the earlier sections, we learnt one electrical property of a material, namely resistance. In the case of time invariant, not changing with time, current, it may be the only electrical property of interest. However, if we consider currents, which keep changing with time, the word resistance is to be replaced by the word impedance. This ever-changing current is called alternating current or AC. It is explained further in the next section. Impedance has a resistive part and the remaining could be either capacitance or inductance or both. Inductance, while inductance is associated with every conductor, it is easily manifested in the case of a conducting coil. When such a coil is exposed to changing magnetic force field, an electromotive force, EMF, voltage, is generated at the terminal of the coil. In fact, this is how generators work. Inductance is that property of a coil by virtue of which an EMF is induced in the coil when the magnetic flux linked with that coil is changed. The change of flux may be due to changing current or AC. Frequency is the number of times the current completes the cycle of change in 1 second and is denoted by F. The measuring unit of inductance is Henry, H. It is denoted by L, inductive reactance, effective opposition offered by inductance. Capacitance, an assembly of two conducing plates separated by a dielectric, is called a capacitor. A capacitor can store electrical charge and in this process offers impedance to the flow of changing current or AC across it. Of course, a non-changing current, direct current or DC, cannot flow across a capacitor. The capacity to store charge is called capacitance and is denoted by C. Its measuring unit is farad. Capacitive reactance, effective opposition offered by a capacitance, is called capacitive reactance, A. It is denoted by XC and it is equal to 1 divided by 2 pi FC, where F is frequency, impedance, the total opposition offered by a series circuit containing resistance, inductance and capacitance is called impedance. It is denoted by Z, where Z equals RJX. Its measuring unit is ohm. In this X denotes reactance due to inductance or capacitance, or A, combination of both. R is the resistance. J is the symbolic representation of square root of 1 or under root minus 1. This is called imaginary number and is used in the calculation of complex equations in relation to electricity. Using this representation of impedance, the associated current also has two components, real and imaginary, or active and reactive. We will deal with this in the next section. Point 1.2.73 Types of electrical loads. Devices that are connected to the power system are referred to as electrical loads. The three load types are resistive, inductive, and capacitive. Resistive load. Units of electrical power associated with resistive load are watts, light bulbs, toasters, electric hot water heaters, and so on are resistive loads. Inductive load. Inductive load require a magnetic field to operate. All electrical loads that have a coil of wire to produce the magnetic field are called inductive loads. Examples of inductive loads are hairdryers, fans, blenders, vacuum cleaners, and many other motorized devices. The units, measurement, of inductance are called henries. Regarding electrical motors, a load placed on a spinning shaft to perform a work function draws what is referred to as real power, i.e., rotating watts, from the electrical energy source. In addition to real power, reactive power is also drawn from the electrical energy source to produce the magnetic fields in the motor. The total power consumed by the motor is sum of both real and reactive power. The units associated with reactive power are called positive vars. VAR stands for volts amps reactive. Capacitive load. A capacitor is a device made of two metal conductors separated by an insulator called a dielectric, i.e., air, paper, glass, and other non-conductive materials. Dielectric materials become charged when voltage is applied to the attached conductors. Capacitors can remain charged long after the voltage source has been removed. Examples of capacitor loads are TV picture tubes, long extension cords, and components used in electronic devices. The units, measurement, of capacitance are called farads. Similar to inductors, the power associated with capacitors is also called reactive power, but has the opposite polarity. Capacitors have negative vars. Negative vars of inductors can be cancelled by the positive vars of capacitors. Capacitors cancel out inductors in electrical circuits and improve system efficiency. 1.2.8 DC and AC voltage/current, direct current, DC. We take the example of a battery, as in a car electrical circuit. The potential difference or the voltage across the terminal of the battery is, more or less, a steady value. The current flowing through any point in the car's circuits is also a steady value, and essentially does not change as a function of time. This is direct current or DC. Working with DC is simpler as we deal mainly with resistance of the circuits. It is rare to have to provide for reactance. The mathematics gets simpler, however. DC has limitations when we have to provide for heavy currents in long distances, as is usually the case with transmission of electrical power in our day-to-day life. Alternating current, AC, as against the DC, we consider the case where the voltage, as also the current, changes as a function of time. We shall consider only the case where this change follows the shape of a sine wave. The voltage/current increases from a zero value to a maximum value, then reduces back to zero, continues down to a minimum value equal to the maximum value, but with negative sign, and finally rises back to zero. This constitutes a full cycle, which repeats thereafter. The number of cycles per second is the frequency, f. Being a sine wave, the value at any time point may be expressed as the trigonometric function sin, whereas an angle with a value between 0 and 0 to 360 degree. Unlike DC, reactance plays a major role in the case of AC. This form is capable of being transformed to higher or lower voltage. This property is very useful for transmission and distribution networks. As stated, AC voltage and current both follow sinusoidal waveform, both have to have the same frequency and are related by the Ohm's law. However, the start of the cycle may not coincide for the two. The difference is denoted by an angle. This is named as the phase of the current. The phase value 0 means the waveforms coincide. Any other phase value points to a reactance in the circuit, i.e., reactance changes the phase of AC. 1.2.9 Active and reactive power. As we have learnt, every circuit current has two components, active component and reactive component. Sometimes, it is easier to see this relationship graphically. Basically, resistors dissipate energy in the form of heat. The power associated with resistive loads is expressed as watts. The power associated with capacitive and inductive loads is expressed as vars. As it is reactive power, the VR is what less power and does not contribute to real work functions. However, vars are required in motors, transformers, and most coils to produce magnetic fields in order for the inductive load to function. The interesting factor that exists in AC power systems is that inductive vars are opposite of capacitive vars and can cancel each other out if they are of the same value. The graphical means of showing the relationship between the real and reactive power associated with resistors, inductors, and capacitors. The term cos theta is called the power factor. January 2nd. 10 Power factor. Efficiency of a power system can be viewed as how much total power, i.e., real power reactive power, is required to get the real work done. Typically, power factors above 95% are considered good, i.e. high. The power factor, PF, may be defined as cosine of the angle between voltage and current. Power factor equals R upon Z equals resistance upon impedance. Power factor equals real power/total power. If the reactive power component is made 0, the power factor becomes unity. January 2nd. 11 Magnet. Some of the properties of magnets have been known for many centuries. The ancient Greek discovered an iron ore called lodestone which, when hums from a thread, will come to rest always pointing in the same direction. This was the basis of the magnetic compass, which has been in use since about 1500 BC as a means of navigation. The magnetic compass is depending on the fact that a freely suspended magnet will come to rest pointing north-south. The ends of the magnet are said to be poles. The pole pointing to the north is referred to as the North Pole and the other, the South Pole. It is now known that a compass behaves in this way because the Earth is itself a magnet. You may like to note the following important aspects about magnet. Magnet is the substance having the property of attracting iron and its alloys, i.e. ferromagnetic material. Every magnet has two poles, north and south pole. These two poles can never be separated. If a magnet is broken into pieces, each piece becomes an independent magnet. Like poles repel each other, unlike poles. attract each other. Its magnet is freely suspended. It comes to rest pointing roughly towards Earth's geographic north and south directions. There are two classes of magnet. Natural magnet, the magnet found in nature. Its mineral name is magnetite. Artificial magnet, the magnet prepared by man-made methods, is called artificial magnet. It is classified as A. permanent magnet and B. temporary magnet or electromagnet. Permanent magnet, the magnet which retains its magnetic properties for a long period, is known as permanent magnet. Any change in its properties comes about only on account of some external cause, e.g. great shock or heat. Temporary magnet or electromagnet. A temporary magnet is a piece of some ferromagnetic material. In its normal state, it does not show any magnetic property. However, by subjecting it to some external magnetizing influence, it gains magnetic property. As soon as the external influence is removed, the induced behavior also vanishes. The simplest external influence is the presence of a powerful magnet in the vicinity. Of interest to us is the use of electricity to create an electromagnet. By putting the temporary magnet inside a conducting coil and passing a current through the coil, the magnetic behavior is manifested. As soon as the current is stopped, the magnetic behavior also vanishes. Such an electromagnet is very useful part of a magnetic crane or inside a generator or a motor. 1.3 Summary. We have learnt about basics of electricity and magnetism. Electricity is basically measured in terms of voltage and current. We saw the difference between direct and alternating current, DC and AC. AC, voltage and current keep changing with time, and if we were to draw a graph, the voltage or the current would be shown as a sine wave. Ohm's law defines the relation between voltage and current passing through a material. The ratio of voltage to current is the impedance of that material or circuit. In case of steady-state DC, the impedance is same as the resistance. However, in all other cases, we have added possibility of inductance and or capacitance being added to the circuit, leading to a complex value of impedance. In this case, there could also be an angular difference between the voltage and the current. This difference is the phase, and cosine of the angle is named as the power factor. We have learnt the types of magnets. We also understand that electricity passing through a coil produces magnetism. On the other hand, a changing magnetic field crossing a coil produces voltage across it. Thus, electricity and magnetism are related. In fact, these two topics are normally addressed together under a common heading, namely, electromagnetism. Electromagnetism helps us to understand the working of generator for producing electricity as well as working of motor to produce force for providing motion to the rotor. There are other diverse uses, e.g., electromagnetic cranes, magnetic levitation trains, etc. Electricity is an extremely useful form of energy. Only, it is not available in nature in a useful form. We produce electricity, transmit it over long distances, and distribute it to be used productively. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.